Michael Schuldenfrei is a National Instruments Fellow focused on long-term innovation for product analytics at NI, which is now part of Emerson. He supports various other activities, including software strategy, sales, marketing, product planning, and R&D, and evangelizes enterprise software solutions to customers. He joined NI from Optimal Plus, and he was there for over 15 years as in various leadership roles, including Chief Software Architect and CTO. And prior to Optimal Plus, he was at SAP and Microsoft. So we welcome Michael.
Thanks very much, and thanks for the opportunity to present today. So I'm going to talk a little bit about the experiences we've had over the last few years with some of our semi customers implementing some of these concepts of real-time AI in high-volume test environments. Sorry, presentation's not really, yeah. So if we look at where the world is today with AI, and I think this was covered a little bit by some of the presentations before, AI as a concept has been around since the 1950s. But the thing that's now making it much more realistic as a tool that can be used in our industry to improve for the various different things that people have talked about in the previous sessions. First of all, there's a lot more knowledge out there about how AI can be used. There's all of the compute capabilities that are available both on the cloud and in-prem. There's hardware produced by NVIDIA and other companies that makes it possible to deploy AI running on large volumes of data and with relatively easy deployment and relatively low cost. There's also, of course, this growing demand for it. The fact that we're in this discussion today all focused around AI. Every conversation we have with customers, there's some aspect of AI or machine learning that people are asking about, or most recently generative AI. So there's definitely a lot of discussion going on that topic. And finally, as we just saw in Ken's presentation, and we've seen from other vendors as well, the AT vendors are obviously also very aware of this trend and are building capabilities to enable real-time inferencing at the edge. So if you put all of those trends together, you're getting a significant opportunity for semi-manufacturers to improve their products in many different ways by leveraging this new technology. And like with any type of new exciting technology of this kind, if you don't adopt it, your competitors will, and you'll get left behind. So we're definitely seeing a significant push now by all of our customers to bring AI to the table and actually do real things with it in a production environment. Ken also showed a list that's similar to this, so I won't go into any more details. But just like Advantest is seeing, we're also seeing a tremendous number of applications that either we've come up with or our customers have requested. Some of these are already productized applications from our perspective. Others are projects that we work with our customers to deliver. But in the end, there's a tremendous amount of things you can do both in semiconductor manufacturing and even further downstream in electronic products that are built using the chips that we're building. So all in all, there are plenty of reasons why people would want to use AI. And very often this AI needs to happen at the edge. In other words, where the product is actually being tested or manufactured, because you want to take action in real time. It could be anything from rebinning to adaptive tests, changing the way the test program executes, etc. And therefore, it's not good enough just doing this as an academic exercise on the cloud. It's something that has to be pushed to the edge. So just some examples out of that list of things that we've already done with this in recent years. For example, scratch detection, identifying scratches on wafers and then binning out the dies surrounding those scratches automatically. You can do it obviously within wafer sort, but you can even do this based on data coming from final test by feeding it back after the fact and then rebinning the parts when they go through an additional insertion. The concept now effectively includes scratch detection as an extended capability as part of an overall outlier detection solution. So when you detect a scratch, you can automatically ink out the parts that are near or integrated as part of that scratch. Examples around managing equipment on the floor. A lot of equipment now gets additional sensors which enable you to view things like vibration, pressure, and so on. Being able to monitor waveforms that are being generated by those sensors enables us to leverage ML and AI to do things like predictive maintenance and understanding issues that are going on the equipment, and also correlating those issues with the specific parts that were being manufactured or tested at the time these anomalies occurred. Another example is next operation optimization. This is an example from the assembly of ADAS cameras going into cars at an automotive tier 1. Without going into too much detail here, you have a whole sequence of processes that are happening to an assembly of camera lenses as they're going through the assembly line. There's lots of inputs that go, or outputs that come out of those different processes, even things like the torque and angle of screws going into the assembly and so on, all of which can impact overall quality. The ability to predict units that are going to fail before the final test or before the final assembly step, and then based on that prediction actually decide whether or not to perform that additional step and save cost and time on parts that are going to fail, has tremendous value in that particular example. So again, what we've seen at NI is that many different parts of our supply chain can benefit from leveraging AI to solve these kinds of problems. So it all sounds like a really great idea, and we can see, as we saw both in this presentation and in Ken's presentation before, there are many applications where it makes sense to use AI. So the big question is, why isn't it really happening frequently and at scale? And the answer perhaps goes into the complexity of building and deploying solutions that are based on AI and ML. Machine learning has a life cycle, and there are 4 key steps, right? The first step that everyone talks about all the time is the training or learning phase, where you're using data to understand a particular issue and build a model that can then be used to predict an outcome. But if you actually want to productionize this particular model, you then need a method and the ability to actually deploy it and perform that action. So, for example, if you want to rebin parts based on the outcome of an AI model, you need the ability to deploy that model into the production environment and actually perform that change. And that can involve either connecting to the ATEs or connecting to MES systems and so on. It's a non-trivial exercise. Another issue is that as products mature and evolve over time, the models which were trained on the early data can actually become stale, and it's necessary at all times to go back and validate the data going into the model and also the outcome of the model to make sure that the model is still functioning as expected. And of course, if needed, and this frequently does happen, if the model needs to change, then you need the ability to adapt that model, retrain it, redeploy it, and then again you go into the circle, going round and round again, learn, act, validate, and adapt. And that eats up a lot of time for the data scientists who are charged with deploying all of these new AI-based solutions in their organizations. So if you look at each of those 4 parts of the ML lifecycle, each of them has its own unique challenges. So at the training level, data scientists, if you talk to them, will all tell you that one of the biggest wastes of time that they have to deal with is just getting the right data, organizing it, connecting it all together, making sense of it, extracting features from it that actually make sense. And in the end, they want to use the tools that they're used to developing with to create their models. It might be Python, it might be any one of a different set of tools that are available out there today and highly popular. Once they've created that model and they have a model they can rely on, they then need to deploy it. It's extremely complicated to deploy it, even if you own your own factories. But in today's distributed semiconductor manufacturing environment, where you typically have companies outsourcing their assembly and test processes to very often tens of different test houses, doing that is extremely complex, extremely time-consuming, extremely difficult. And by the time you finish doing it, your model is stale and your product is probably no longer bleeding edge. As we said before, actionability. If the model needs to make a decision that actually impacts either the binning or the process of that particular device, then that needs to be either connected back to the test program or it needs to be connected into the MES system. Again, that requires a level of complexity which is very far from trivial. As mentioned before, if you own your own, if you're an IDM and you own your own manufacturing facilities, it's one level of complexity. But if you need to do this across a distributed supply chain where you're outsourcing a lot of your assembly and test, it becomes next to impossible. The validate part is also extremely challenging. How do you validate a model's performance when you're manufacturing millions of parts across multiple geographies, right? You need to be collecting all of that data. You need automation to be looking at that data and making decisions. And what you need to do is you need to prevent the technical debt building up where data scientists are constantly working just on maintaining their existing models as opposed to developing new models and creating more value for your organization. And finally, once again, even if you've identified the fact that you need to adapt your model, you now have to retrain it. You now need to go through that whole process again. You very often, you're going to want to have some kind of human in the loop, some kind of ability for a user to look at the data, look at the outcomes, and provide additional input as to whether the process is actually working as expected and as required. And finally, of course, there's the relearning process itself, which is often manual, time-consuming, and so on. So actually deploying ML-based solutions in a production environment for high-volume semiconductor test is very far from trivial. And we're not the only people who are saying that. There's this highly recommended article from some engineers at Google back in 2014 called Hidden Technical Debt in Machine Learning Systems. And the point that they're making is that the machine learning code development part, this little black box in the middle, is really the smallest and easiest part of the whole exercise. The cost in managing and maintaining AI-based solutions is actually in the infrastructure that surrounds it, handling all of the different aspects of collecting data, moving data around, managing the model deployments, and so on. So if I go back a little bit to my roots at Optimal Plus, which as was mentioned before, is now part of NI, which in turn is now part of Emerson. The solution we developed back in the early 2000s, is for a centrally controlled system that enables data collection and interaction with test programs at the edge. On the left-hand side here, you can see those different OSATs or manufacturing or test facilities where the system is deployed. It includes a piece of software called the proxy, which is actually running on the tester, enabling real-time interaction with the tester. It has the ability to collect data and manage data within each of those factories. And then all of that data can also be aggregated to a central system at headquarters, enabling engineers to view the data, analyze the data, but also then deploy rules back to the system at the edge, which in turn, again, are integrated back into the tester itself, into the test program, and into the MES systems in the various factories. Now, when we built this system, we weren't thinking AI. In the early 2000s, AI was still a concept that was a long way away from where most test organizations were going. This was purely around things like outlier detection, OEE, etc. We weren't really thinking machine learning at all. But when you think about it, this kind of solution actually does check the box for all of these different aspects of managing infrastructure for machine learning solutions. And I won't go exhaustively through all of the boxes because we're a little bit restricted in time, but just to give some examples of what I'm talking about. If we look at the box called feature extraction, right? You have your raw data, which is something you might want to use to build a model from. But it's not just about providing that raw data to the model. You also want to provide intelligence to the model. A really good example is, for example, XY coordinates of die on a wafer. You can provide a machine learning model with the XY coordinates, and the machine learning model can try and go and make sense of that and find some kind of correlation between those coordinates and all sorts of effects that are being seen on the wafer. However, everyone who's worked in the semiconductor industry knows that more important than the XY coordinate themselves is actually the distance of that die from the center of the wafer, right? Because that particular location information or information about which reticle it's in or which location in the reticle can actually be much more meaningful than simply the XY coordinate. So a system like LiCo+ or systems like the ones described before in some of the previous presentations are able to derive all of these derived engineering features from the raw data and save the data scientists a lot of time in preparing the data to as an input to that model. So that's just one example from the Learn arena of how this kind of system speeds up the process of actually building and deploying solutions that do ML. Another issue that customers have is there are many ways to build a machine learning algorithm. Unless you have some really smart data scientists with the time and bandwidth to build those models, it can be a daunting task. So we've come up with a set of solutions to simplify that process for users and budding data scientists who want to actually build solutions using AI, but don't necessarily have the expertise to do it all manually. And the way that works is, first of all, of course, data is generated and it's already typically stored in the solution like the O+ solution. It's then extracted directly to a notebook. The AutoML application then accesses that notebook and trains a whole variety of different models to predict a specific outcome that the user is trying to predict. Once that is done, the system can then display various different options or different algorithms, combinations of algorithms which produce the best result tuned to the specification that the user is trying to achieve. That algorithm can then get deployed again using a Docker, just like we saw in the previous presentation. And the notebook is created and can be deployed automatically to the edge using the same deployment mechanism that we talked about before. We talked about the fact that one of the key areas that are important for leveraging AI at the edge is the ability to get the rule into the test program or connect it to the test program or the MES system in a way that actually works. And for that, we have the O+ rule system. You can create a rule either as Python code that's running inside a Sequoia script. Sequoia is our analytics programming language that's embedded in our system. Or you can just have it in a container and have the system deploy the container for you. But the whole concept of process management, of actually getting that rule to the edge where it can actually process data and perform actions with the test cell, is all part of the rule engine that existed well before we had AI-based solutions. And once you have a solution that's running AutoML, one of the things you need to be able to do is constantly analyze that outcome, as we saw before in the validation part of the flow. And you need to make sure that there's no drift or change in either the input parameters going into the model or the output of the model. If there are, they can be detected automatically using the rule engines in the system. And the system is then able to come up with different alternative models and predict or produce a model which can give you better results than your existing model, and automate the entire process of then recycling that model and redeploying a new model in place of the older one, which has gone stale. Then also we have the whole concept of human in the loop. As we said before, one of the big problems that AI has today is that there is a certain level of distrust between engineers and an AI model. It's difficult to believe that an AI model that you don't fully understand its inner workings is actually going to provide the kinds of results that I expected. It's not going to overkill or underkill yield, for example. It's not going to miss quality issues that I'm looking for, and so on. So one of the things that we built into the system is a UI which enables users to evaluate the outcome of a model that's executing at the edge, and then reclassify the answer or make recommendations back to the model to fix the results effectively that the model itself predicted. If we take an example where we're using it for binning, you can see here a system where a wafer is going through wafer sort, that's generating wafer maps which are loaded into the database. The AI model is making a prediction which creates a classification for the die. But before actually generating that final ink map, those results are diverted to a user who can view those wafer maps, view the suggestions and recommendations that are being made by the model, and if necessary, change that decision. That change decision then becomes the final result that is sent to the ink map, which then goes to assembly. But it's also used and fed back to the AI engine so that the model can be retrained and incorporate that feedback from the user, from the expert user. So going back to the list of challenges we saw before, if we look at what's now possible, and this is stuff that many of the large semiconductor organizations are already using in production today. On the learning side, we've fully automated the process of getting all of the data, aligning that data, and providing it to the data scientists so that they can do their job most efficiently. It automates the process of extracting all of those features. We talked about the distance of a die from the center of a wafer, or its location in a reticle, and so on. On the acting side, we are already deployed in almost all of the subcons worldwide, certainly all the large ones in Asia, which means we're already connected to the MES systems, we're connected to the testers, the proxies running on the tester as well. So we have all of the capabilities to integrate the real-time actions that the technology promises into test programs and into the actual manufacturing and test processes. On the validation side, we have a rule engine which is already able to monitor all of the different parameters. I didn't go into detail on that in this presentation, again, due to a lack of time. But if anyone's interested, I can provide a lot more information on the kind of things we look for and what the capabilities are in that area. And that in turn reduces the technical debt. So in the end, the engineers who are working and building these solutions can move on to the next one and not remain stuck with the one that they've already deployed into production. And finally, on the adaptation side, we have the ability to identify stale models, the ability for users to interact with the outcome of the model, and the automation or partial automation of relearning, again, depending on the preference of the data scientist. And where is all of this going next? So our solution that's based on our proxy, which enables communication through the test program, can only take us so far. For example, it doesn't give us prober and handler control, some of the stuff that Ken talked about in his presentation before. So we're already working today, both with Advantest and with Teradyne, to connect their real-time execution engines with our ability to gather data, move that data around, make it available for the various models, and also to provide all of the analytics tools to the users who want to build those models and generate these kinds of applications. We're working with them, with Teradyne. We've already published a partnership a few months ago, and with Advantest we're in advanced stages of setting that up as well. And we will have these capabilities built into our system, so you can choose whether you want to use the engines that are built into the NI Optimal Plus solution, or you can use the engines that are built into the ATE themselves. Either way, the system can support all of those kinds of operating models. That covers what I have to present. Again, if anyone's interested in more information, please feel free to reach out to me, and I can also connect you to our AI teams who are experts on building solutions based on all of this. And thank you again for the opportunity to present. Open up
Thank you. Thank you, Michael. Let's see, are there questions? I have a bunch, but as usual, but happy to take some from the audience. So just use the Q&A tool. Also take a minute, please give Michael some feedback. So you talked about one of your applications, you know, predicting failures before they're actually tested bad. where you're looking at the prior operational data to predict parts that are bad. And you touched upon, okay, yeah, you need to update your models and things. But when you're looking at this and you're preemptively declaring something to be a failure before you actually measure it, I'm assuming you convince the customers and the users by demonstrating. You take a reference lot, you run it, you say, hey, these are going to fail, and then you get the failure data and you say, yeah, look, with a certain correlation they did fail. It's probably high 90% correlation, otherwise people probably wouldn't use it. But how do you know over time something hasn't drifted? So let's say they turn this on in production and they let the software bin out the stuff without actually running it to know that it was bad. How do they know it doesn't drift, or how does it, over
That's an
time?
excellent question. I actually referenced it a little bit when I was talking, when I was showing the slide that was talking about the human in the loop application. Although I didn't actually talk about it too much, it appeared on the slide. It goes back to this whole issue around confidence in the model, and you're absolutely right that the drift is, or process drift is one of the things that sort of creates this level of mistrust in that process. So there are multiple ways that the system solves that today. One way, as I said, is we actually monitor the input parameters that are going into the model, right? In many types of models, you're able to get some kind of level of explainability that tell you what are the key features that impact the decisions that the model is making. We can then constantly monitor those parameters to see if anything significant is changing in their behavior. Are they drifting? Are they moving perhaps more towards their limits or whatever, which could in turn raise questions about the quality of the model that's executing. Another thing that happens is typically there's a lot of sampling going on. So let's say you have a model that's going to predict that you can skip test for a bunch of parts. What you're going to typically do is you're only going to skip the test for, let's say, half of the parts that the model is predicting. And the other half at the beginning, you will test. And that way you'll be able to determine whether or not the prediction is correct. And over time, you can reduce that sampling rate, but you'll always leave some level of sampling in the process so that you can catch those kinds of drifts and changes that you're talking about. I would also say that it's very rare. I think that I can only remember one case where a customer really went to the extreme of using a model to totally skip a test phase or to make a final decision on binning. What they typically do is they use it to tune the level of test that's going to happen at the next insertion. That's particularly powerful, for example, when going into burn-in, right? You can actually reduce the amount of burn-in you're doing on many of the parts if you have high confidence that they're not going to fail at burn-in.
Makes sense. A good question here from Phil. Thank you, Phil. How close are we able to read in a structured data set, e.g. from ATE data logs with headers, and be able to ask questions verbally only and get technically useful responses?
That goes back into the generative AI question. We've actually been playing around with that quite a bit. We have a demo application that we built, which can take. I think I actually have a video of it somewhere. If you want to send me an email afterwards, I can send you a link to the video. For example, you can ask the system to build an outlier detection model for you that looks for parts that are 5 sigma away from the center line. Please create the script for me, and the system will just create the script. So those are the kinds of automated generative AI-based solutions that we're already playing with. NI more broadly has a language model called Nigel that they're using to develop test programs and so on. They've been presenting that in the last year or so. So we have several teams that are currently working on solutions around that. I will say that from everything I've seen so far, there is still quite a lot of work to be done to get these systems to provide outputs with high enough quality. At the moment, the amount of human interaction that's needed afterwards to fix problems with the algorithms or models that generative AI is producing is still quite significant. So there's a way to go. But obviously, NI and I think probably everyone else in the industry are all busy working on that problem today.
Makes sense. And you've seen a number of production projects. I mean, who's typically building and managing the AI model? Is this more workload for the test engineer, or now you need an army of data scientists, or what are you actually seeing in customers that are implementing your systems?
So we're actually seeing quite a broad cross section. We've got some customers who have dedicated data science teams whose role is to look at test data and implement improvements to the overall test process using AI on test data. So in those cases, our typical interaction is going to be with the product engineers and with that data science team. We have several customers who are already doing this completely independently. So they're just generating and building their own containers, Docker containers, and they're using our platform as the platform to deploy them to the edge. We also have customers who are leveraging NI's product team, right? We've got a bunch of experts who are both experts on semiconductor tests and also experts on AI ML. We have a team of data scientists who are dedicated to those kinds of projects, and we provide those services to some of our customers. But we're seeing more and more and more customers who've understood that they need to double down on their investments in AI and bringing in data science teams and trying to do this on their own.
Okay, great. Well, Michael, I thank you for a great presentation. Let me take the screen back. I would like to thank our sponsors once again, ASC and Amcor. And with that, I will wish everybody a great rest of their day and look forward to seeing you at a future MEPTEC event. Thank you for joining us.